So the first time I discussed the right-hand rule, I told you that the right-hand rule has nothing to do with the physics. It is really mathematics, okay? It's that when you have two vectors and you want to find the direction of the cross product between these two vectors, you use the right-hand rule. Any two vectors, this can be in mathematics and whatever, chemistry, in engineering, okay? This is a general rule. Now, today we're going to see how to add sine waves by using what you call the phasor diagram, okay? That would be like the only thing which is really new. And the rest is relatively, is going to be much more straightforward once you know the what's resistance, what's the capacitance, and what's the inductance. I think that, as I will highlight here, even though when we're doing these AC current circuits, okay, the continuous usage of Kirchhoff laws in solving problems, okay? It's the same thing. So when we talk about circuits alternating, what are we talking about? An alternating current or alternating voltage or alternating circuit is the one where you have an AC generator. This means that it's the direction of the current which changes, not the amplitude, okay? So the direction which goes in one direction would go like this, let's say clockwise, and another time it goes counterclockwise. When this happens, so the direction changes, okay? That's what we call an alternating current, okay? Basically, it's as if you have a battery which goes minus plus at some time and then plus minus at other times, okay? So the battery is changing and the voltage is changing. Once again, this is not related to the amplitude, but more to the direction. So, for example, you see here clearly there are three examples of DC currents. Of course, when you put a battery and it's a 5-volt battery, for example, we know that it's DC. But also, when this battery, the voltage or the current oscillate as a function of time, even they go from 0 to some maximum value and back to 0, we are still in a DC world, in a DC current, okay? AC is that when you have this dashed line is 0, so at some point the current or the voltage is in one direction and the other one is in the other direction. For example, if you take the square wave, okay, the current value is exactly the same. Okay, the value of the absolute value of the current is exactly the same. What it changes is only the direction. Okay, just to give you an idea, really clear idea about what AC signals are. You have triangular waves, sawtooth waves, and of course, sine waves. I'm going to go quite rapidly on the characteristics of the sine waves. So we have the amplitude, X max, so this is the maximum value. We have omega, which is equal to 2 pi f, which is the angular frequency. Angular, we'll come back to that in the phasor diagram. So basically, if you have a circle, a circle, okay, and it's really angle, refer to the angle. The angle with respect to the x-axis. So you have, that's your x-axis, okay, this is your x-axis. That's your angle here, okay. How fast this angle changes is your angular frequency, okay. So it's radian per second. So radian is the angle, radian per second is the angular frequency, or basically how fast this angle is changing. Is it slow or is it fast? Okay, equal to 2 pi f, where f is the frequency, t is the period, okay. One important thing that I would like to highlight is the phase. Usually it's not well understood. The phase indicates the value of the signal at t equal to 0. So for example, if you take a sine wave, okay, sine of omega t plus phi, so if you set t equal to 0, this means that you are at this value here, okay. What you have x equal to 0 is equal to x max, which is the amplitude multiplied by sine of phi. So phi equal to 0, then x of t equal to 0 is equal to 0. If phi is equal to pi over 2, then x at t equal to 0 is equal to x max, etc., etc. So it really sets the value at t equal to 0. Now the phase is important, is more important for when you compare two signals than for the signal itself. If you have a sine wave, as it's shown here, then this sine wave repeats itself. So basically, then the question where I put my t equal to 0 is a choice. You can put it at when the signal is equal to 0, or when the signal is at the maximum, or anywhere in between. But once you set this reference, the t equal to 0, then this is going to be set for the others as well. And now the phase is going to play an important role, as we will see shortly after. So if now I compare two signals, okay, I have two signals, xa and xb as function of time. X base is equal to x max sine of omega t plus pi over 2. Xb is equal to sine of omega t. So in order to see, let t equal to 0, so this is your t equal to 0, you see that xb is equal to x max sine of pi over 2 is equal to 1. Consequently, your x of a is maximum, okay? Whereas your x of b is equal to 0. In this case, we say that a is ahead of b, or a leads b by 90 degrees, because there's 90 degrees. The question about 90 degrees, it goes back to the angle. So once again, this is my 0 angle, okay? And this is my, this is 0 angle, okay? And so the phase difference between the two is 0. Now, when this goes to 90 degrees, all right, this means that it's 1/4 of a lambda, because your signal goes back exactly where it was after 1 lambda, right? So if I go back here, so after 1 lambda, after 1 wavelength, or after 1 period, okay, the signal goes back exactly to where it was, and then it repeats itself, okay? Now, at half a lambda or half a period, okay, you are at an angle equal to pi. At a quarter of a period, you are at an angle of 90 degrees, okay? So there's an equivalence between the sine of omega t, which is in time like this, and the angle, okay? For this reason, when we say a pi over 2 phase shift, this means that signal 1 is 0 and signal 2 is at maximum. Now, when it is a pi phase shift, this means that the signal 1 has, let's say, plus pi over 2, and signal 2 has minus pi over 2, okay? And when the two are exactly in phase, then the sine of omega t plus pi over 2, and sine of, for the B signal, sine of omega t plus pi over 2. Okay, so the phase, the role of the phase is really much more to compare one signal with respect to the other, and to see whether one is leading, they are in phase, opposite in phase, or lagging. Okay, for example, if you take the first example here, A is ahead of B, or A leads B, or we can say that B lags A. Okay, it's behind it. Okay, so I hope this issue is clear. So now let's go into trying to see what happened if I put a delta V max sine of omega t in series with a resistor. In order so the question is, I've given you delta V, give me the current I. Okay. Well, to do so, then I use Ohm's law. Okay. Delta V around the battery is equal to delta VT, which is equal to delta V max sine of omega t, and I have R. So basically, I of t is delta V divided by R. So delta V max divided by R sine of omega t, because here delta V is sine of omega t. Consequently, I can define I max to be delta V max divided by R. And the phase difference between the current I and potential V is equal to 0, because in Ohm's law, it does not change the phase at all. If I start with sine of omega t plus any phi, then I'm going to have for I of B equal to delta V of sine of omega t plus this phi. So the phase difference between the current and the potential is exactly equal to 0. Now, if we move on for the capacitor, okay, so we're going to use delta V in the battery is equal to delta V of the capacitor. But delta V of the capacitor is equal to Q divided by T. So on the left-hand side, I'm going to have delta VT, which is delta V of the battery, equal delta V of the capacitor. This is using the conservation of energy. All right. Now, the delta V of the capacitor is equal to Q divided by C. Since my delta V is time dependent, of course, my Q, the charge in my capacitor, will also be time dependent. Consequently, I can deduce that Q is equal to C multiplied by delta VT. What's delta VT? Delta VT equals delta V max sine of omega t. So consequently, my Q is equal to C delta V max around the capacitor, if you want, sine of omega t. Okay? Now, what is my question? I want my current. My current is related to the charge by dq over dt. Consequently, I of t is equal to C delta V in the capacitor C, d over dt of sine of omega t. D of the dt of sine of omega t is going to give me omega cosine of omega t. So consequently, now I'm going to say C delta VC omega, this is my current I max, okay? And I'm going to rewrite cosine of omega t as sine of omega t plus pi over 2. Consequently, now I have the amplitude I max, which is equal to C delta VC omega, and I'm going to have a phase difference between the current and the potential equal to plus pi over 2. Now, it's very interesting to say that delta VC is equal to ZC multiplied by I max, okay? So here we cover also Ohm's law, okay? Because delta V is equal to a constant multiplied by, equal to a value multiplied by I max, that's Ohm's law. With ZC is equal to 1 over omega C, okay? Now, this resistance, this effective resistance or impedance, what we're going to call it, impedance, not only depend on the capacitor value, but also depend on the frequency. Okay, and we'll come back to that in a few seconds. So on the other matter, which is the phase difference, delta phi equal to phi I minus phi V equal to pi over 2. In this case, we say that the current leads the voltage by 90 degrees, or the voltage lags the current by 90 degrees. But that's the outcome of when you're putting an AC generator with in series with a capacitor. This is the response that we have. Finally,
So the phase,
yes,
the phase angle is given, right? I know for us to know the phase difference.
The phase angle of the voltage is given is equal to 0.
Yes, but how would we know that the current is 90 degrees behind the voltage?
Because I of t is equal to dq over dt. Okay.
Okay.
Okay. So so basically, you start from here. I of t equal to dq over dt. What's q? Q is here, right? Is given by C delta V max sine of omega t. So what you need is just, this is constant, and what you need is derive this as function of time. The derivative of this as function of time give you an omega, and also give you a cosine. The cosine, if you want to compare the voltage to the current, you need to put it as a function of sine, because your voltage is a sine of omega. Okay?
Oh, okay, okay.
Simply rewrite the cosine as sine of omega t plus pi over 2, and this is where my phase comes to play. Then for this reason, phi I minus phi v is equal to plus pi over 2. Clear?
Yes, yes, thank you.
To all you guys, please do not hesitate to put your unmute yourself and then to ask your question. Okay, so let's continue with the inductor. Okay, so now I'm gonna put a inductor instead of the capacitor and try to see the response. Okay, once again, I'm gonna have a voltage. Okay, this is my voltage. Sorry, this is my delta V max sine of omega t. That's given, and L is given. So how would you calculate once again, use delta V around the battery is equal to delta V around the inductor. Delta V around the inductor is equal to LDI over dt, okay? Consequently, delta V of the battery minus LDI over dt is equal to 0. This is once again conservation of energy, okay? So now I'm gonna write di as equal to 1 over L d delta V multiplied by dt. It's the same thing coming from here. So delta V is equal to LDI over dt, or di is 1 over L delta V multiplied by dt. I integrate di between 0 and t, and I integrate this value between 0 and t. Okay? So now all the constants will get out. So delta VL is equal to delta V max. We're gonna write it like this, delta VL equal to delta V max. Okay, and now I of t is equal to delta VL. The integration of a sine of omega t is gonna be equal to 1 over omega minus cosine of omega t. Okay, once again, if I want to compare the sine of omega t here to what I get, I need to put the minus cosine as sine of omega t minus pi over 2. Okay, and now I'm going to have I max equal delta VL divided by L omega, or delta VL equal to ZL multiplied by I max, which is basically Ohm's law, with ZL equal to omega L. And the phase difference phi I minus phi V is going to be equal to minus pi over 2. So once again, what I was able to do is I was able to calculate the current, given that I'm going to have just one inductor which is in series with the AC voltage generator. In this case, we have the voltage will lead the current, and the current will lag the voltage by 90 degrees, because I'm going to have a minus pi over 2 phase difference. Z is impedance as the impedance, okay? The capital Z and L is called, we will see that in a few seconds. ZL or XL is called the inductive reactance. ZC or XC is called the capacitive reactance, and ZR and XR is called the resistive reactance. Okay? That's it. Now, note that it's very important now. XC and ZC, the unit is in ohm, not in the, so 1 over omega C is C is in farad, omega is radian per second, but the ZC is in ohm. Why? Because if you look at this equation here, okay, that's Ohm's law. So delta V is equal to RI. So whatever you multiply the current, it will have the unit of an ohm. Okay. So this is what's the case here. And now if you go on and you look at what happened to the capacitor, okay. Okay, this is also what you can see here. That's also Ohm's law. Okay, consequently, the unit of ZC is an ohm, okay, and it will act like a resistance, but it's not a resistance. To give you an idea about this acting like a resistance, but not a resistance, assume that I have, instead of, assume that my capacitor is fully charged, okay? What's the current which is flowing in my system is going to be equal to 0, right? Because it's fully charged. So basically, this capacitor which is fully charged, it will act as if I put a resistor, but the resistor, the value of the resistor is extremely high. Okay, so it's basically it's the same. If I have a capacitor which is fully charged with resistance with resistance which is extremely high. Okay, so this gives you an idea how come the 1 over omega C is an ohm. It's basically paying a rho resistance, but this resistance is not in the form of collisions of the electron with the atoms, but is in the form of a charging and discharging of a capacitor. I hope this is clear. Okay. Now what we're going to do, we're gonna put 2 signals in series. For example, here a resistor and a capacitor. Okay, and of course we're going to use Kirchhoff laws, which is basically the conservation of energy in this case here. I don't have a junction, so my current is the same. Very important. My current is the same, and the potential difference of the resistor and the capacitor is not the same as that of the battery, but the conservation of energy tells me delta V of the battery is equal to delta VR plus delta VC, exactly to what we did before. And now I'm gonna treat the resistor as if it's all alone, and the capacitor as if it is all alone. But the problem comes in the following: the resistance does not add any phase to my signal. So if I start with, let's say, I equal to I max sine of omega t, delta V in the resistor will be in phase with the current I. Okay? And the capacitor, it will add a pi over 2 phase difference. So now if I want to use this method here, okay, which is delta V equal delta VR plus delta VC, which is the time, I'm going to be confronted with adding 2 sine waves with different phases. Okay? And now we come into this, what you call the phasor diagram. What is the phasor diagram? The phasor diagram is a general way which will allow you, okay, to add sine waves with different phases. Okay? I'm going to stop a little bit here because we have less than a minute. Okay? And ask you, do you have questions to what we saw so far?
No, sir, thank you.
It's clear. So, so basically, let me just. So how about the inductive reactance? What we said, the capacitance is at the charging. Remember, L will play a role only when I have time variation, and it will act as a battery. Okay, so at best, so as if I have a battery minus plus, and here plus minus. Okay, so it will impede the motion, it will resist the motion by actually reducing the potential difference about the real battery by adding another battery which is in the opposite direction. And it will always be in opposite direction because it will always oppose the change. So when it's going up, it's going to oppose the change, or going down, it's going to oppose the change. Okay, so generally speaking, the inductor will oppose the